Perfect. Perfect. All right. So Dr. Sujudi could not make it today. I'm going to moderate this session today. Thank you, Dr. Zhang, for being here and accepting this invite. So if I want to give a fair bio of Dr. Zhang, it's going to take quite a bit of time today. So I'm going to make it short. Dr. Zhang received his bachelor's and master's degree in structural engineering from Tongji University in China, followed by a PhD degree in mechanical engineering in LUT in Finland. And he has worked for almost a decade before joining the NTNU in one of the largest research centers in Europe, working on fracture mechanics. He has visited several universities, including Harvard University, University of Science and Technology in Beijing, Kyoto University, and Caltech. And without any delays, I'll give you Dr. Zhang. Thank you.
Thank you, Omid, for the kind introduction. Today, I will talk about how to lower the ice adhesion by promoting macroscopic crack initiator. As you see, I'm from Norwegian University of Science and Technology. Please allow me first to give you a very short introduction about my university. Maybe not everyone is familiar with Scandinavia. So here, let's have a reference. Here is, do you see my mouse? Do you see my mouse?
Yes.
Yes.
Okay. Here is UK. And across the North Sea, here we have Norway. And here we have Sweden, the Scandinavia countries, Denmark, and we have Finland. Here is Russia on the east side. And my university, NTNU, that's the Norwegian University of Science and Technology, is located in the middle of Norway. A city called Trondheim. It's a small city. So here is Oslo, the capital of Norway. It's NTNU is the largest university in Norway. We have about 40,000, over 40,000 students. We are producing more than one PhD every day. So it's about 400 PhDs a year. And there is one number very special with our university I would like to share with you. So if you go to the industry in Norway, if you pick 10 engineers, master engineers, 8 of them are from our university, NTNU. So this is a very special position in Norwegian industry. Okay, here is my outline today. So I will briefly introduce my research lab called the Nanomechanical Lab. And then I will tell you everything what I know about ice adhesion. I will talk about super ice adhesion surfaces. Specifically, I will talk about the flux mechanics-based design principle to achieve super ice adhesion surfaces. And I will end my talk with some perspectives. Okay, let's go. Here is the overview of NTNU Nanomechanical Lab. I established this lab in 2006. And now we have 3 faculties. Me and Professor Jin here in the middle are professors, and we have a new associate professor, Chen Bo Xiao. And in the last 10 years, the number of PhD students in our lab has been quite stable. So we have about 10 to 15 PhD students. and we have 2 or 3 postdocs, and we have some visiting students. The main theme of our research are nanomechanics, fraction mechanics, and interface engineering. So if we divided our research activities, we can roughly divide it into 4 research domains. I have a strong fraction mechanics background, so we have been working on structural integrity of mostly on pipelines. You know, Norway is the energy country. Norway has, except Russia, Norway is the only country in Europe who produce a lot of oil and gas. So Norway has 8,000 kilometers underground pipelines connecting Norway and rest of Europe. So we have been working on fraction mechanics problems to secure the safety of these pipelines. And a recent topic we have been working on is hydrogen embrittlement. Hydrogen embrittlement becomes very important, not only in Norway but also in many other countries because of the perspective of green energy. Hydrogen as an energy carrier holds great promise for the future. The second one, which is related to my talk, is my talk today is so-called smart phobicity. This is just the opposite of fraction mechanics. You know, the purpose of fraction mechanics we have been working in the last 20 years is to secure the safety of structures and components, to make the structure safe. However, in the smart phobicity research, we are doing opposite. We want to use the same principle in fraction mechanics to destroy the interface between the ice and the solid, between the snow and the solid, between the gas hydrate and the solid. So this is the same principle, but just a completely different purpose. One is to secure the structure, another is to destroy the interface. The third one, because Norway is an oil country, so in the last years we have been trying to bring the nanotechnology to the oil industry, which is a very conservative industry. So we have been looking at the possibilities of using nanoparticles to enhance the oil recovery. I mean, there is a kind of possibility. The nanoparticles, for example, genus nanoparticles, that means particles have 2 phases, were diffused to the triple junction between oil, water, and solid, and to enhance the disjoining pressure. So we have been carrying out quite a lot of simulations to understand how the nanoparticles can influence the flow, disjoining pressure, and adhesion, wettability, etc. The last one, we have a fantastic nano lab at the NTNU. So we have been using the nano lab to fabricate, to design materials with special functions, special properties. For example, last year we have reported in the advanced materials were the toughest elastomer. This is one of the examples. Okay. Let me show you some research highlights before I going to talk about the ice adhesion. So here, not a long time ago, for the first time, we combined the self-healing property and anti-aging functions together to design and fabricate self-healing anti-aging surfaces with very low ice adhesion. In the beginning, it's between 4 and 6 kilopascal. The long-term ice adhesion is between 10 12 kilopascal. This is healed surface. The ice adhesion is about 14 kilopascal. You know, most of the anti-icing surfaces, they are of static nature. So we, for the first time, introduced dynamic anti-icing surfaces. That means the interface is not static. Interface will change with time. So this dynamic anti-icing surfaces will have very low ice adhesion. Also, you see there is evolution in the interface between ice and solid. So this is a kind of a new concept in the smart phobicity. Very recently, we have introduced so-called Oni-inspired gas hydride surfaces with the hydride adhesion 2.9 kilopascal, very low hydride adhesion. So today I will also mention a little bit gas hydride as well, not only ice. So talking about anti-icing, I think it's interesting to mention the world record in icing of power line. You know, Norway is a cold country, and icing is quite common. So icing on the power line could be a very beautiful scenery. It could also be a catastrophe. So there is a world record in icing. The diameter of ice on a power line, the world record is 1.5 meter. The weight approaches 300 kilometers per meter. Such heavy loads, additional loads, can easily cause collapse of the power line. So this is a world record. So we want to get rid of the ice. There are two possible means to get rid of ice. First is called de-icing. That's an active method. De-icing, of course, we can use heating, we can use mechanical forces, we can use chemicals. However, these methods either need energy or will pollute the environment. So these are not wanted. On the other hand, it would be very, very preferred, very nice to have a passive anti-icing method. In general, there are 3 different categories or strategies to develop passive anti-icing surfaces. First one is to get rid of the water. So to repair the incoming water droplets, we can play the surface energy, we can play the surface texture, structure. I will talk about that later. So if the surface is dry, then there is no ice, no concern for the ice. Okay, so this is the first strategy. The second one, of course, to suppress the ice nucleation. So even we have water, we can suppress the ice nucleation. So either we can lower the nucleation temperature or delay the nucleation time. There is a lot of research in these two aspects. Unfortunately, no matter how hard you try, when the time is long enough, when the temperature is low enough, ice will come to the end. So the strategy we have chosen is to live with ice, but with the lowest possible ice adhesion. Ice adhesion it's called ice adhesion strength, in fact. The definition of ice adhesion is if you have ice on top of a surface, if you want to remove the ice, you just put force. The maximum force to remove the ice divided by the cross-sectional area. This is in this case it's the shear ice adhesion strength in shear. Of course, we can make tensile. We can make tensile testing. So this would be the ice adhesion in tension. I want to mention that ice adhesion depends on many factors. It depends on the testing methods, testing conditions, temperature, loading rates, and also depend on the type of ice. This is interesting factor, and we have spent efforts to understand the effect of type of ice on the ice adhesion. So we collaborated with AMIL in Canada, Chicoutimi, and we fabricated 3 types of ice. We have precipitation ice, we have impact ice with the speed of 15 meters per second. We have bulk ice, and this ice will have different density. So bulk ice will have largest average density. Then impact ice is in the middle. Precipitation ice has the lowest density. What we found is that the ice adhesion strength is inversely proportional to the density of ice. This was a very surprising result. In fact, no one believed that. It was very difficult for us to publish this result. But once we have published, then everyone is citing our paper. So we have got a lot of citations on this paper. So ice adhesion depends also on the type of ice. Now we have talked about ice adhesion. Then the next question is, how low is low enough? I want to give you some numbers about ice adhesion strength. The tensile strength of ice is between 700 to 3,100 kilopascal. So that's the tensile strength of ice. The measured reported ice adhesion in the literature between almost 0 to 1.5 megapascal. For a typical metallic surface, the ice adhesion strength is larger than 600 kilopascal. For non-textured, fluorinated surfaces, let's say polymer-based, the ice adhesion is larger than 200 kilopascal. There is a definition in the literature. If the ice adhesion strength is below 100 kilopascal, then this surface is called isophobic surface. And we have a definition. If the ice adhesion strength is below 60 kilopascal, we call this surface called low ice adhesion surface. We have some reasons. I will show you next slide. In addition to the low ice adhesion surface, we have a so-called super low ice adhesion surface. So if you have one ice cube, 1 cubic meter of ice, if it can fall down automatically by its own weight, the ice adhesion strength is approximately 10 kilopascal, and we call this value super low ice adhesion surface. And this was one of our targets to develop surfaces to achieve this kind of value. Okay, let me show you the reason why we define 60 kilopascal as the low ice adhesion surface. I have been asking a question to my students. If we know the room temperature characteristics, can we predict the ice adhesion, which is low temperature? That means if there is any correlation between room temperature property and low temperature property. We have tested 22 different coatings. We found that when the ice adhesion strength is high, for example, is higher than 200 kilopascal, there is a correlation between the low temperature ice adhesion strength and the room temperature weightability. This is the same as what we have seen from the literature. However, when the ice adhesion is below 60 kilopascal, it does not correlate with the room temperature weightability anymore. It does not correlate with the surface roughness as well. Does not correlate with the hardness. However, low elastic modulus does not guarantee low ice adhesion. On the other hand, surfaces with low ice adhesion always have a low elastic modulus. So these are the correlation between room temperature property and the low temperature properties. What we found is that when the ice adhesion below 60 kilopascal, there is a kind of correlation between the ice adhesion strength and the water adhesion force. So here we see this is below 60 ice adhesion, and in this region, the water adhesion is very low. So I will talk about the correlation more. Another question we have been asking ourselves, for the same surface, for example, for the same metallic surface, aluminum or steel, is there any correlation between atmospheric ice, that means fresh water ice adhesion, and sea spray ice adhesion? The question is, if we know the atmospheric ice adhesion, can we predict the C-spray ice adhesion? If these two ice adhesions are not the same, which one is larger? I don't know any of you have any answers to this question. Let me give you the answer. C-spray ice adhesion is about 100 times lower than atmospheric ice adhesion. For example, typical metallic surface, for example, aluminum, the ice adhesion would be 600 kilopascal. If we talk about C-spray ice, the ice adhesion will be less than 5 kilopascal. So this is a big contrast. For the same surface, we have 2 orders of magnitude difference. Another question, maybe many of you know the gas hydride. Anyway, Dr. Suyudi knows the gas hydride. He has been working on the gas hydride. Gas hydride is a problem for the oil industry. So the question is, for the same surface, if we are talking about the aluminum surface, if we know the ice adhesion, can we predict the gas hydride adhesion? Which one is larger? We can plot vertical axis as the ice adhesion. Horizontal axis is the hydride adhesion. Ice adhesion is 5 times larger than the gas hydride adhesion. And this is both experimental observation and also molecular dynamic simulation. I think this relationship are very interesting and very useful for the engineering design. Okay, we have talked a lot about ice adhesion. We want to have a lower ice adhesion, as low as possible. But how to lower ice adhesion? We have many possibilities. We can lower the elastic modulus, we can lower the surface energy, we can introduce lubricating liquids, use the interface slippage, surface texturing, many methods. The question is it possible to fatally weaken the ice-solid interface and further lower the ice adhesion? Yes, there is a method. So we have an interface here between the ice and the surface. If we make a crack, this certainly will weaken the interface. We have an analytical formula which tells us that ice adhesion strength, ice adhesion strength, tau c, is proportional to the square root of elastic modulus multiplying the surface energy, inversely proportional to the crack size. So you can imagine if we have a crack, we have a crack here. If we have a small crack, if we have a large crack, certainly the ice adhesion will be lower for the case with a large crack, right? So the purpose to weaken the interface can be realized by maximizing the clock length. So we have based on this understanding, we have proposed a fluctuation mechanics based super low ice adhesion design principle. So what you see here, we have vertical axis, that's the ice adhesion. We have 100, that's isophobic. We have 60, that's low ice adhesion. 10, that's super low ice adhesion. And on the horizontal axis, that's the receding contact angle. So we can see that we have a correlation between low temperature property, that's isophobic property, and the room temperature property. So let's see the correlation. To begin with, we can divide the space into 3 regions. First, we have a hydrophilic, and then we have a hydrophobic region, and then we have a small region that's called superhydrophobic. So we cut these into 3 regions. What you can see that there is a magic dot. There is a magic dot. This is a very interesting position. It's located at ice adhesion close to 200, between 180 and 200 kilopascal. Horizontally, it's about 120 degrees. So this is a point I want to explain. So above this point, that means when the ice adhesion is larger than 180, we have a very good correlation between the ice adhesion strength and the receding contact angle. This is for smooth surface. So for the smooth surface, no matter how hard you try, I mean, this is controlled by the surface chemistry, surface energy. No matter how hard you try, you will not overpass this point. So we call this, all the factors influence this curve. We use a name called the nano crack initiator, NACI. That's controlled by nanoscale defects, van der Waals, electrostatic interactions, hydrogen bonding, etc. So the main effect of these nanoscale initiators is to weaken the interface. But no matter how hard you can try, it stops at this magic point. If you want to go any further, for example, if you want to go down, go to the low ice adhesion region or super low ice adhesion region, you have to use the so-called micro crack initiator. That means you have to use surface you have to texture your surface, build the surface structures, such that, for example, when ice forms, we have air trapped at this roughness. So here we have a micro crack. This will function as the macro crack initiator. We call this MISI. However, you know, waters in many cases can weight the surface, even the roughness. So once we have a weighting at the valley, then when we have interlocking, ice adhesion will increase rather than decrease. So this MISI approach is not stable. We have been asking ourselves, do we really have to go through this MISI path? Can we go another path? For example, can we go down directly from anywhere to the super low ice adhesion surface region? From here? The answer is yes. So what we can do is so from here you can see here we have done something on the smooth surface. Here we have done something on the surface structures. One thing what we have not done yet is the subsurface structures. So we introduce so-called macro crack initiators, MASI. So we can do something about subsurface structures. We can build the property gradients vertically. For example, if you have this kind of subsurface structures, when you shear the ice, you will generate cracks at the interface between ice and the surface. So we can theoretically prove this MASI concept. For the homogeneous coating, homogeneous surface, if there is no subsurface structures, usually for a 2D problem, we have 2 crack initiation sites. So crack could possibly initiate here on the left and here on the right, the 2 initiation sites. If the length of the ice becomes larger, the total length of crack size over the air, when the air approaches infinite, it becomes 0. So there is a crack length could be neglected. However, if we have subsurface structures, if we do something with subsurface structures, we have multiple crack initiation sites. If we do the limit, the total crack length over the ice length will be constant. You see, this is the difference between the case with MASI and without MASI. Now we have the theory. We want to prove our theory. So we choose the PDMS and try to fabricate MASI surface. We have choose different structures. This is D is the width, the same as spacing D here. So we have a single layer, we have a double layer. So we have bottom layer 67 micrometer, and we change the H as well. We use our lab to fabricate the coating. I'm not going into details here. These are the coating we have fabricated. So if you do something with the subsurface structure, we got immediately 50% reduction in the ice adhesion. So this is a very, very simple structure we have done. We can change the spacing and the width d from 10 micrometer to 100 to 1 millimeter. It seems 1 millimeter we can get 80% reduction of the ice adhesion. We can have a double layer. If we use double layer, we get additionally 1/3 of reduction compared with the single layer. So here is an overview of the mass effect. So we change the H. H is the height of the top layer. So we change from 30 micron to 150 micron. Mass mechanism has so huge effect. This is for single layer, and double layer is even more significant. And we can also change the cross-linking density of the PDMS. By changing the cross-linking density from 333 to 162, we go to coatings, so-called Zhiliang surface, far below the 10 kilopascal we intended to as our target. So we go on. We also fabricated a so-called sandwich sponge with unprecedented ice adhesion strength around 1 kilopascal. This is the case without any oil, without any lubricants. If you put other lubricants, certainly it will be even lower. Okay, that was about Marty. Let me see. I think I have used up my time. Let me summarize. Here are the take-home messages. There are 3 mechanisms to weaken the ice-solid interface: NACI, MISI, and MASI. MASI is a very powerful tool to lower ice adhesion, also hydride adhesion. So we are currently working on MASI surface for hydrophobic surfaces. PDMS surfaces, that's MASI surfaces, without any oil or additives, with ice adhesion about 1 kilopascal was demonstrated. And of course, if you want to further modify, optimize the MASI surface, it's possible, because you can easily incorporate other mechanisms into the MASI. So we are working on, in general, so-called repellent surfaces. It covers a wide range of applications, from anti-fouling to anti-snow, anti-gas hydride, even CO2 condensation, etc. I believe this repellent surfaces has a great future. Here are the projects in this specific topic we have been working on. Okay, thank you. Thank you for your attention.
Thank you very much indeed, Dr. Zhang. Thank you. Very interesting. Okay. Any questions? I'm trying to monitor the chat room. Maybe to get it started, I was wondering how resistive these surface coatings are with respect to corrosion and fatigue of the surface of the harsh environmental condition.
VDMS is, I mean, it's not very known about the corrosion and the fatigue. At least to me, it's not very clear. But it's relatively durable. We could enhance the durability by different means. In general, durability is an issue for all the anti-icing surfaces.
Right. Thank you. Please.
One or two quick questions. Thank you, Dr. Zhang, for your talk. It's quite interesting, and I see a lot of application, especially in our region, Ohio, with cold winters. My question is about this interface Young's modulus, that it is technically a constant in your tau equation. How do you measure or calculate this interface Young's modulus? Is it a material property? I'm wondering how this, because when you talk about Young's modulus, it reminds me of tensile testing Young's modulus. Is this like you do some sort of like peel testing or some type of testing to figure out what is the interface Young's modulus?
Maybe I have not made it clear. This equation, this one, right?
Right, exactly.
This is E star. This is a combination of the ice modulus
Okay.
and the coating modulus.
Okay.
So it's a combination of ice modulus and the coating modulus. Ice modulus is known.
Okay.
So it's a function of a coating modulus indeed.
Okay. And how do you experimentally, how do you measure it?
We can easily measure the coating modulus by nano indentation.
Oh, exactly. Like a scratch testing or things like this.
Yes.
Okay, now got it. Now makes sense. Yeah. My other question is about the exact same equation here. This delta boundary dependent constant. Would you be able to please elaborate a bit? What is this and how to calculate it? It's a material property again. What is this constant?
No. The delta is not a material constant, it's a geometric constant.
Okay.
So it's case dependent.
Okay. You mean a substrate, right?
Yeah, I mean, it depends on what kind of shape of the crack. If it's circular or it's elliptical or
Okay, now makes sense. Okay, this is technically that lambda, because we show it here with lambda. This is what we have in fracture mechanics. I thought this is something different. Anyway, thank you so much. I'm good. Thank you, Dr. Zhang.
Thank you.
Thank you, Maisan. Thank you. There is a question in the chat room, Dr. Zhang. The question reads, have you studied fatigue behavior besides the tensile behavior of the original specimens versus the coated specimens? So a comparison of the fatigue behavior for the coated surface?
No, unfortunately, we have not. But fatigue, I mean, fatigue is not particularly a concern. It's the durability which is a concern. I mean, fatigue, you need a fatigue loading. The loading is not very high. It's the durability. It's UV. It's thermal expansion. These kind of issues are more important.
Right. So it's more of like a surface attachment, scratching, the durability as opposed to the surface fatigue, right?
Yes.
All right. Any other questions? Please feel free to unmute yourself or just write it in the chat room. Well, if not, I thank you again for accepting this invitation to talk to us.
Thank you.
I hope someday you can visit us in person, and I thank you on behalf of.
Thank you. I hope.
All right.
I'm looking forward to it.
All right. Thank you, everyone. Have a wonderful break.
Thank you.